Hello and welcome to today's problem solving session for this course. Uh, we'll wait for a couple of more minutes if there are more participants to join. Okay, we'll start. So today is the sixth week's session. I hope I'm audible and my screen is visible. If you can put your comment in the chat box, please do that. So we'll be dealing with the sixth week's lecture contents and questions related to that, which is basically going to help you solve the 6 weeks assignment problems. And the lecture is based on, the problem solving session is based on the lecture series from 25 to 29 on law of groundwater movement, Darcy's law and its application. So we'll move on to the problem solving part. Okay, so moving to the first problem. The law of flow of water through the soil was first studied by uh, which person? Is it Taylor, Darcy, Jordan, or Lamb? Put in your answers in the chat box, and after that, I'll be discussing the solution. We had learned about this Darcy's law in the previous. This has been provided in the previous lectures, as well as solved a couple of problems related to Darcy's law. So I'll go to the answer. The law of flow of water through the soil was first studied by Darcy. Correct answer is option B. So Darcy's law is a basic equation in hydrogeology, more importantly in groundwater hydrology. And Darcy's equation, so-called Darcy's equation, is giving a relationship between the velocity of flow of water in an aquifer as a function of the hydraulic conductivity, hydraulic hydraulic gradient, as well as the cross-sectional area. So moving on to the next question. You can put in your answers in the chat box. Coefficient of permeability or simple permeability is expressed in terms of what unit? What is the unit of coefficient of permeability, or you can also call it as permeability? The other word for it is hydraulic conductivity. So what is the unit for this quantity out of these four options? Put in your answers in the chat box, and then I'll discuss the solution. So the correct option is option D. So let's see why. We know hydraulic conductivity, coefficient of permeability, or this permeability is also called as hydraulic conductivity. Hydraulic conductivity can also be defined as the velocity of flow of water through the media at unit hydraulic gradient. Now, we had learned about what Darcy's law is. Darcy's law is giving us that the velocity of flow of groundwater is a product of the hydraulic conductivity and hydraulic gradient. Hydraulic conductivity or coefficient of permeability or permeability being depicted by this letter K, and I is the hydraulic gradient. Hydraulic gradient is nothing but the difference in the pressure head to the length of flow of water. Now, say if this hydraulic gradient is equal to 1, then what happens is V will be equal to K. So that this is how K is obtaining the units of velocity, which can be centimeter per second, or it can be meter per day, or feet per day, or any of these. It will be expressed in terms of the uh, units of the units of velocity. So this is the definition of hydraulic. This is another definition of hydraulic conductivity. That is, it is also defined as the velocity of flow of water through the excuse me through the porous media at unit hydraulic head. So the correct answer for this question will be option D. Next question. What kind of flow is Darcy's law valid in? Is it valid for laminar flow, turbulent flow, hydraulic flow, or all of the mentioned? Correct? So Darcy's law is valid only for laminar flow. So let's see what laminar and turbulent flow are. So laminar flow is a very quite slow moving water flow that is characterized by water moving in straight line in parallel layers, whereas turbulent flow is characterized by very erratic movement of water and very fast movement. So this is how we depict laminar flow and turbulent flow. In real life, you can see if you open the tap, water will flow from the tap in a very straight manner, and that kind of flow is called laminar flow. And the flow that, I mean, as a result of the splashing of water that happens as a consequence of opening of water into sink or wherever, this kind of erratic movement of water is called turbulent flow. So Darcy, when if you look into Darcy's law is only valid for laminar flow. It is not valid for any kind of flow. It is only valid for flow which is laminar in nature. Now, Darcy's law is a very prominent law when it comes to groundwater flow. So, what is happening in ground when water is flowing through aquifers or porous media in the ground are in fine grained material. The pores are very small and they're close by, so water will flow slowly through them in a laminar nature. Again, in coarse grain material also, it is going to behave similar to a laminar flow, but when the size of the material is very huge and the pore spaces are very large, then this flow is going to be a bit mimicking a bit of a turbulent nature. So Darcy's law is only, I mean, if you want to calculate the velocity of flow of water, it is only possible if that flow occurring is a laminar flow and not a turbulent one. And also here it is only valid for slow viscous flow where the Reynolds number is going to be less than 1. If the Reynolds number is less than 1, then we can say that it is a laminar flow. So these are the general assumptions of Darcy's law. The soil has to be saturated. You can't just unsaturate the soil and some movement of water in partially saturated soil is not possible. The soil has to be saturated. Flow should be laminar. The flow should be continuous and steady. That is, there shouldn't be break in the flow of water. Steady as in the properties of water flow, like the velocity will not be changing with respect to time. Steady state flow, and the whole cross sectional area of the soil has to be considered. If we're just considering a small part of the soil, then this Darcy's law is not valid for that portion alone. It should consider the whole cross sectional area of the aquifer material or whatever porous media that is for which you're calculating the velocity or discharge. The total cross-sectional area has to be considered. So Darcy's law in this question, the option A would be right. It is only valid for laminar flow. Moving on to question 4. The coefficient of permeability is equal to velocity under which conditions mentioned here? Correct. So we had earlier seen that coefficient of permeability can also be defined as the velocity when the hydraulic velocity of flow through a porous media under unit hydraulic gradient, which means hydraulic gradient is equal to 1. So the correct answer is option A. If the travel distance of tracer between two wells is 15 meter and the required time for the tracer to travel between these two wells is 3 hours, what is the actual velocity of the tracer? I see. Okay, great. Let's move on to the answer. So what we are talking about here is actual velocity of the tracer. So I would like to discuss these two terms, actual velocity of the tracer and traveling time of water. So if they ask you what the traveling time of water through this porous media or the groundwater flow is, it is basically the ratio of the distance traveled by water or the length through which the water is traveling to the velocity of groundwater times the porosity of the material. So if they ask you for the traveling time of water, we can't just divide the length by velocity. We have to multiply it with the porosity of the aquifer material. And not only that, usually traveling time of water is expressed in year. and the velocity of water has to be given in meters per day and traveling distance in kilometer, and this will and multiply with the porosity, and you will get the traveling time in year. So here in this traveling time of water, what you have to be careful about are the units, as well as multiply it with the porosity. Actual velocity is nothing but the distance traveled by the tracer, and excuse me. So it is the distance traveled by the uh, tracer, and to the time required for the tracer to travel between these two wells. So here the correct answer would be 15/3, which is 5 in meter per hour. Here also the answer is in meter per hour, but in case if it was given in some other unit, you would have to do the appropriate unit conversion to get the answer. Moving on. Which of the following factors affects the permeability of the soil? Okay, so let's see what are the factors that are affecting permeability. Now, permeability can be given by this equation, which is a product of a constant C, which is taking care of all the soil properties, into the square of the effective size of the material, into this unit weight of water by viscosity and the void ratio. So from this equation, sir, we can understand that it is depending on the effective size of the material, the diameter of the particle, size of the particle. It is also dependent on the properties of water, and it is also dependent on the void ratio of the material. C is units, factors that are taking care of other properties of the soil. So from this equation itself, we can understand what the permeability will depend on. Again, grain size distribution, soil texture, soil structure, porosity, shape of the particle, arrangement of the pores, property of the pore fluid, and as well as it's not just water that is going to be there in the pores. Sometimes there is air also going to be there in the pores, or carbon dioxide gas and all. So that it will also depend on the properties of all of that. So in this case, all of the mention, it is dependent on the grain size, it is dependent on the specific surface area of the particles, it is dependent on the void ratio of the soil. So option D will be the right answer. What is the mathematical representation of Reynolds number given as? So for all the new joinees, you can put in your answers in the chat box, and then I'll be uh, dealing with the solutions later on. Okay. So Reynolds number, it is a quantity that is discussing what kind of flow is happening. We had talked about what laminar flow, what turbulent flow is. So how do we recognize mathematically if a flow is laminar or turbulent? Laminar flow is when the Reynolds number is up to a certain range, and turbulent flow is when the Reynolds number is of another value. It is basically the relationship between the inertial force and the viscous force of the fluid. And mathematically, it is given by this formula rho v d by mu, where rho is the density of the fluid or water that is flowing. V is the velocity. V is the seepage velocity, not just the velocity of flow, but the seepage velocity. D is the size of the grain material, the effective size of the material through which water is flowing, and mu is the dynamic velocity, dynamic viscosity of water. So this is a mathematical representation for Reynolds number, and Reynolds number is a ratio of the inertial force and the viscous force. So the answer for this would be option D, inertia force by viscous force. Next, which of the following statement is true for the relation between discharge velocity and seepage velocity? So for the earlier Reynolds number, I had mentioned that the value V is the seepage velocity and it's not the discharge velocity. So discharge velocity is the velocity that we're talking about in Darcy's law and all. So what is the difference between that? Okay. So let's look into the different kinds of discharge velocity and terms that has been described in the lecture series. So we are talking about seepage velocities. If you see, seepage velocity is the hydraulic conductivity, product of the hydraulic conductivity, the hydraulic gradient divided by the effective porosity, whereas Q is equal to again hydraulic conductivity into the hydraulic gradient. Now if you see here, Q is nothing but this big Q by A. Big Q is the total discharge, A is the cross-sectional area, when Q by A is equal to small q, and that small q is called the specific discharge. So if when A is taken down here into the LHS, this whole term Q by A becomes small q, and that is called the specific discharge. So total discharge is one term, specific discharge is another term. Seepage velocity, if you see, we know that velocity is discharge velocity is given by V is equal to K into I. But when the effective porosity is also taken into consideration, then that term is called as the seepage velocity, and it is different from the discharge velocity with respect to the fact that porosity is also considered. Now, seepage velocity, what does it mean in physical senses? It will be when you take a particular part in this entire medium where for which you're considering the Darcy's law. Say we want to calculate the velocity of groundwater flow through this entire medium, then that velocity is given by the discharge velocity. But say we want to take the velocity of flow through a series of pores that is forming one small path. Then what we do is we take into consideration the porosity of of this material, and then calculate the seepage velocity through the series of flow. So this is always going to be greater because we are only taking the lesser cross sectional area, so it is definitely going to be greater than the velocity of water flow. So the correct answer in this case would be, so when you take velocity, it is going to be discharged by area. So uh, lesser the area, more will be the velocity. So in this case, seepage velocity can never be smaller than the discharge velocity. So the correct answer would be option B. Moving on, is seepage velocity inversely proportional to hydraulic gradient? Is the statement true or false? Excuse me. Okay. So the correct answer would be option B. Again, because discharge velocity, whether it is discharge velocity or seepage velocity, it is directly proportional to the hydraulic gradient. But inversely, seepage velocity is inversely proportional to the porosity of the material. There is no difference in the placement of the hydraulic conductivity or hydraulic gradient. Seepage as well as discharge velocity are directly proportional to the hydraulic conductivity and hydraulic gradient. So in this case, the option B, the statement is false. Moving on, what are the types of water flow that can occur in the soil? Okay. So the correct answer is option A. Earlier I had mentioned the possibility of linear flow is no, nil in terms of water that is flowing through the soil. The flow can be either laminar or it can be turbulent flow. Laminar flow, like I said, in materials like clay, where clay or coarse grained materials, when the pore spaces are small, the flow will occur in a laminar. The flow will be of laminar nature, but when the pore spaces are huge, as in very huge boulders or material comprising of boulders or huge rocks, the flow can be turbulent. So turbulent as well as laminar flow is possible in soil, but linear flow is not possible. Moving on, what is the coefficient of permeability of fine sand? This is 10 to the power minus 6, 10 to the power minus 2. Okay. So this part of the portion you'll have to memorize because I don't see any other way. So coefficient of permeability as the size decreases varies in this way. For very clean gravel material, it ranges from 1 to 100 centimeter per second. And as the size reduces, it goes, it keeps on reducing. 1 to 0.01, fine sand is 0.01 to 0.001, silty 0.001 to 10 to the power minus 5, and clay is less than 10 to the power minus 6. So here they're talking about fine sand. So it is 10 to the power minus 2 to 10 to the power minus 3. These two options are very close, but I think the upper limit is 10 to the power minus 3. So this will be the more correct answer. Next question. What do you call the energy possessed by uh, fluid by virtue of its position? Is it called the pressure energy, elevation energy, dynamic energy, or both A and B? Let's just briefly go into the each term. So pressure and elevation energy are both forms of potential energy, which is described, or which is a function of the position of the fluid. Elevation energy is when the energy that you calculate at a level of the fluid above the mean sea level or above a particular datum. Pressure energy is the energy that is as a result of the density and the properties of water. If you're considering water, it is as a result of the pressure exerted by water. Now, both of them are dependent on the position or position of the both of the forms of energy are dependent on the position of the medium. So that is why pressure and elevation energy, and the third form of energy is the velocity head or the kinetic energy. It is also called the velocity head, dynamic head. So these are the three terms for the velocity head, or the energy that is possessed by water by virtue of the movement of water, by virtue of its velocity, which is called kinetic energy as well as dynamic energy or dynamic head. So the correct answer in this case would be both A and B, pressure energy and elevation energy. So the three forms of energy that is possessed by water is pressure energy as a result of the pressure exerted by water, elevation energy as a result of the position of the water from the mean sea level. Both of them are a function of the position of water. We also take into consideration the level of at which water is in pressure energy as well as in elevation energy. Dynamic energy is a function of the velocity of the water. So these are the three forms of energy possessed by water that is giving it its total energy. Now, this is giving us the expression for the total energy of water. Here I've mentioned what each terms are representative of. E is the total energy per unit height, or energy per unit head. It's not energy per unit weight, it is energy per unit head. Is it equal to V square by 2G, P by rho G plus Z, or which of the expression is true in this case? Okay. Option A and C are common, so yeah. So yes. So the energy per unit weight or energy per unit head possessed by water is given as a sum of the velocity head, the pressure head, and the elevation head. This is also called as the dynamic head or kinetic head. This is called the pressure energy. And a sum of these two is what we had talked about in the earlier question by virtue of the position or state of water. So if you see in this diagram, the energy possessed as a result of water being at a height of z from the mean sea level or from this datum is what is called the elevation head or the potential energy, gravitational potential energy. Then this is the amount of energy that is possessed by water as a result of the pressure exerted by water, as a result of its density, and as a result of its gravity. And this part is representative of the energy that is possessed by water because of the velocity of flow of water in this wherever water is. So say this barrier breaks, water is going to flow with an energy corresponding to the sum of all these three values. So the correct answer is A. Here C is also giving the same option, so it can be either A or C. Moving on, which of the following defines V square by 2G? So V square by 2G is giving us is the expression for the kinetic head. We had done this in the previous portion. Here we are talking about the total energy of water is a sum of V square by 2G, P by rho G, and Z. Z is the energy possessed as a result of the height of the water, the position of the water above the mean sea level, or some datum from which we are taking the measurement. P by rho g is the pressure head or pressure energy, that is the energy possessed by water as a result of the pressure exerted by the water. And V square is because of the velocity. This is also called as kinetic energy, velocity head, or dynamic head. This we had seen here. These are the different terms that are used for describing this part of the equation, V square by 2g. Kinetic head, dynamic head, or velocity head. This is called pressure head. This is also called the elevation head or gravitational potential energy. This is called pressure head or pressure energy. So these are the different terms that are used for describing all these quantities in this to calculate the total energy of water. This is kinetic head, velocity head, or dynamic head. This is called the pressure energy or the pressure head. This is called the elevation head or elevation energy or gravitational potential energy. So that is why in this question V square by 2g, the answer would be kinetic head. Datum head is another name used to describe elevation head or elevation energy. Moving on, which of the following is defining the hydraulic head for groundwater flow? Okay. So we just now talked about the total energy possessed by water or energy per unit weight by water. And we saw that it is a sum of three forms of energy. One kinetic energy, another is the pressure energy, another one is the elevation energy. Now this pressure energy and elevation energy, those two energy, which is a virtue of, which is a function of the position of the water, is together called as the hydraulic head. So, and in groundwater flow, energy per unit weight can also be called as the groundwater flow energy per unit weight is also called as the hydraulic head, because in groundwater flow, now when we consider the flow of water from a high point in a mountain to a low point in a mountain, there will be high velocity with which the water will flow in case of surface water. But when it comes to groundwater, the velocity with which groundwater is flowing is going to be usually a few meters or few centimeters in 1 year. So it doesn't make sense to take into consideration the kinetic energy. So in terms, when we are calculating groundwater flow, when we are calculating the energy of groundwater flow, usually the kinetic head is ignored. And that energy per unit weight in case of groundwater flow, that is given as a sum of the elevation head and the pressure energy, is called the hydraulic head. So here the correct answer would be option C. Hydraulic head is equal to P by rho g plus Z. What you have to take remember is this is valid for groundwater flow. It is not something that we talk about when we are calculating the energy of surface water flow. And why? Because in groundwater flow, the velocity is going to be very negligible. So it doesn't make sense to take into consideration the velocity. So The energy per unit weight of water in terms of groundwater flow is also called as the hydraulic head, which is given by the sum of the pressure energy and the elevation energy. So the answer in terms of this question would be option C would be the correct answer. So here you need to calculate the velocity of groundwater flow. Uh, the hydraulic conductivity is given, and question says that two piezometers are located at distances 500 meter apart. First point, the water level is 1 meter. Second point, the water level is 1.5 meter. What will be the velocity of groundwater flow? Now we know what is, according to Darcy's law, what is the equation for velocity of water. You know what is hydraulic conductivity. You know what is hydraulic gradient. And all of the quantities have been given in this question. So please do the problem and put in the answer. Let's check the solution. So here they've said that the distance between two piezometers is 500 meter, which is basically the L term in hydraulic gradient. Hydraulic conductivity given is 30 meter per day. Difference in the water level, that is H2 minus H1, or delta H, is given by what is the head at water level at first piezometer and the second piezometer. Difference between those two. So delta H is equal to 0.5. This is the equation for velocity, product of hydraulic conductivity into I. I is nothing but delta H by L. So all of these quantities are given. This is given in meter per day. So 30. Again, this answers are in two forms, either meter per day or meter per second. So we have an answer in meter per day. So for that, we'll put all of the units as it is, and we see that 30 into 0.5 by 500 is 0.03 meter per day, which is there in the option. So because that, we don't have to worry much about the units. So the correct answer for this would be option A, 0.03 meter per day. Okay, moving on. Again, this problem, hydraulic conductivity is given. This is for the same earlier question. Hydraulic conductivity 500 meter apart, 1 meter water level in first point and 1.5 in second point. Here porosity is given. what has been asked is to compute the traveling time of water from the head of the valley to a point which is 15 kilometer downstream. So we know the velocity calculated from the earlier question. What we need to do is calculate the traveling time. And I had earlier shown what is the equation for the traveling time. How is it different from the normal time that we compute? Traveling time is equal to the length by velocity into the porosity. So you just need to remember the units that has to be used in that, and pretty much it's a simple mathematics to do the problem. Okay, so let me take you back to the equation. Here, the traveling time is the distance by velocity into porosity. Distance has to be in kilometer and velocity has to be in meter per day. So in the case of this question, we see that distance is given 15 kilometers. Velocity we know from computing from the earlier question, that is 0.03 meter per day. So porosity is 30%, which is 0.3. So just multiply and also 15. Just, okay. You don't have to actually change all this. You can simply 15 divided by 0.03 into 15 divided by 3. Okay. I mean, unlike what is given in that equation, you will have to make use of the correct units. So if it is 15 kilometers, you have to change it to 15 into 1,000 meters divided by 0.03 is in meter per day, and 0.3 is the porosity, and also you have to convert the meter per day into year and then obtain the answer in years. So the correct answer would be option C. Okay, I have to again confirm for this question because in that they have particularly said that the distance will be in kilometers and the velocity in meters per day. So I'm a little doubtful about why we are changing the units in this case. So let me just confirm that, and then I'll be changing it in the material and posting the material. Okay, moving on. What is the term used to measure the energy of water representing the height to which it can raise itself above a given level? So the hydraulic gradient, hydraulic conductivity, hydraulic head, or hydraulic pressure. We learned quite a bit about the energy of water per unit weight or head, water's pressure energy, elevation energy, and dynamic or kinetic energy. So here they're asking about the energy that is representing the height to which it can raise itself above a given level. Okay. So hydraulic head is combination of the pressure head and the elevation head. This is both a function of the position of water. So even if the position of water is here, as a result of the pressure of water, it is also adding, the elevation is also needs to be added on to this height of the water. So hydraulic head would be the answer. So the correct answer is option C. Height to which it can raise itself is a function of the pressure head as well as the elevation head. And totally, these two quantities are called as the hydraulic head. Now, I think we'll take a break of 3 to 4 minutes. We'll be back here. Now it is 7:01, and I'll restart the session at 7:05 exactly. Okay, so welcome back. We'll continue with the session. So next question. Darcy's law is describing the relationship between water flow rate and what other quantity. So the hydraulic conductivity and elevation head, hydraulic gradient and pressure head, hydraulic head and velocity head, or hydraulic conductivity and hydraulic gradient. Okay. So we all know what Darcy's law is and what quantities it is emphasizing on, the velocity and the flow rate. So here the question is, what is it describing how is it describing the relationship between water flow rate? So water flow rate is usually the product of the hydraulic gradient and hydraulic conductivity as well as the cross sectional area. The options here, the first three options are not possible. It is not talking anything about the energy of water. It is talking about the flow rate as well as the velocity. And in both of those quantities, the flow rate and velocity, what is common is the hydraulic conductivity and hydraulic gradient. So the correct answer is option D, hydraulic conductivity and hydraulic gradient. What term is used to describe a circular depression in water table due to pumping from a well in an unconfined aquifer? Okay. So if you see here, what you can see is when pumping happens, the water is going to follow this curve within the aquifer. It is going to have a particular curve such that the water in this aquifer is going to enter into the pump and the well water is going to keep increasing. And this curve is called the drawdown curve. So if in a three-dimensional point of view, if this is the well and water is being pumped out of this well, water is going to follow this kind of a motion, a radial motion into this well from all the directions. And this curve is called the drawdown curve. This distance between this well and the point until which this curve is being an asymptote or a horizontal line, and there is no angular difference between the horizontal is called the radius of influence, and this uh, uh, circular area that is formed as a result of this radius of influence is called the area of influence. In this question, they're asking about the circular depression in water table due to pumping. What term is used? It's a cone of depression. This is called the cone of depression. This curve is called the drawdown curve. This area is called the area of influence. And this is called the radius of influence. That is the distance from the center of the well and the point until which this drawdown curve becomes horizontal is called the radius of influence. So again here, what is cone of depression? When you're watering the pump, the water is going to go down. Water level around the well is going to go down because water is going to enter the pump. Sorry, the well. So this is forming a cone, like inverted cone, like shape of the water, and this is called the cone of depression. Curve is called the drawdown curve. Radius of influence is the distance from the well to the edge of the cone of depression. Area of influence is the entire area around the well where the groundwater levels have been lowered due to pumping. Area within the radius of influence. So again, this will be the area of influence. This will be the radius of influence. Schematic representations. This is the kind of representation that you get during uh, for problems. This is the cone of depression, drawdown curve, radius of influence, and this distance from the water level to this point from where the cone of depression is starting is called the drawdown distance, and this distance from the mean sea level or whatever is the base of this well to the water level in the well is called the height of the water in the well. We'll be looking further into all of that in the coming questions. So this is also one other diagram that can help you on understanding this cone of depression and radius of influence and area of influence or well. Now, a well is pumped at a constant rate from an unconfined aquifer, and the drawdown curve is monitored over time. And we see that this drawdown curve is approaching a constant position with respect to time. What does this observation tell us out of these four options? Take your time, understand the options, and then Okay. So let's move on to the answer. So again, let's just get a clear idea about the various terminologies that are used if we need to understand this question in a more comprehensive manner. So we talked about what this drawdown curve is. This distance from the static water level, that is when the water level is at its highest pressure before pumping, to the level of the water at present after the pumping has happened is called the drawdown. So that is the height of the water that has been removed as a result of pumping. And it is depicted by SW, which is drawdown in the well. Another quantity mentioned here is the HW, that is nothing but the height of the water in the well measured from below this reference level or datum or mean sea level, wherever the measurement is starting from, to the level of water inside the well is called the height of the water in the well. That is represented by HW, and that is also giving us the hydraulic head. We talked about what hydraulic head is: pressure energy plus elevation energy. That is as a result of the pressure of water inside this, as well as the position of the water from the reference level. So here, since the reference level is starting from here, you can say that this will be the hydraulic head. Now, suppose the reference level is starting at a line that is way below this, you have to calculate that height also along with this pressure energy. This is the radius of influence. That is, you can see that this is the farthest point at which the drawdown curve is becoming horizontal. So that is called the radius of influence. And the height of the water at that level is called the initial hydraulic. That is, initially before the pumping starts, water will be at this level. So the height of water at that point is depicted by capital H. RW is nothing but the radius of the well. R is any distance from the center of the well to a point somewhere over here, and the height of the water in the well at this point from the center of the well. So such a distance of R from the center of the well is given by HR. These are some terminologies that you have to get familiar with in order to not only understand this question but also do problems related to finding the discharge rate in confined and unconfined aquifer. There are problems based on Thiem's equation and Dupit's equation. So these are terms that will be provided in numericals, for which you'll have to find the discharge rate based on these values that are provided. Now here, when it comes to steady state flow in unconfined aquifers, water in an unconfined aquifer is considered to be flowing at a steady state when pumping is happening, means that the drawdown is going to change only as a result of the position of this drawdown curve. Here is only the drawdown height is only going to change as a result of the position of water. Now, if you look at the radius of influence, what the drawdown is, it will be 0. Now, if you come a bit over here, the drawdown will be this much. If you're coming to this distance, the drawdown is going to be S. So this drawdown is not going to vary with time. That is what it means by steady state. So drawdown is always a function of the location when we are talking about steady state flow in of water in wells in unconfined aquifer. Not only that, the soil has to be homogeneous and isotropic, and the flow in the well should be in a radial manner. That is, only then we can get the drawdown curve, the cone of depression, the radius of influence, area of influence, and like usual, it has to have a laminar flow, and the loss of head will be proportional to the hydraulic gradient. So these are the equations that are giving us the discharge rate of water flow in a pump. So what is the rate of flow of water? This given by Thiem's equation and Dupit's equation. Like I mentioned, here R is radius of influence. Small r is the radius of the well. H is the height of the water, initial hydraulic head, and this small h is the height of the water at this point. So if you're taking some distance r1 from here, the height of the water will be h1 there, and drawdown will be s1. And again, another distance of r2 from the center of the well, the height of the water is going to be h2, and drawdown is going to be s2. So in when you have to calculate the discharge rate or the pumping rate through a well at some random distance from the center of the well, you use this equation. Lippitt's equation is used when you have to calculate the discharge rate based on the radius of the well and the radius of influence of the well that is provided. Now let's move on to this question and what these options imply. So if this condition has to be reached, that is, well is being pumped at a constant rate, it is given that it is being pumped at a constant rate, aquifer is unconfined, drawdown is monitored over time, and it is also reaching a constant position with respect to time. That itself says that it is a steady state condition. That is, if the drawdown is approaching a constant position with respect to time, it is the steady state flow through an unconfined aquifer. So for a steady state flow, we saw that the drawdown is a function of location. The medium has to be homogeneous and isotropic. It is proportional to the hydraulic gradient. And one more point was what? Yeah, radial, horizontal, and laminar flow. So option 1 says that the pumping rate is too high, leading to unstable flow conditions, which is not possible because here in the question they have already said that it is a steady flow, that is constant position with respect to time. So there's no possibility of an unstable flow, or the pumping rate is too high, which is also contradictory to the question because here they have said that the well is being pumped out at a constant rate. So it is not going high or low, it is at a constant rate. So this option is not possible. Now, if you move on to the next option, they are saying that the hydraulic gradient is decreasing over time, and that is why the drawdown is approaching a constant value. So let's check, get a little more insight to this option. So we know the difference in the hydraulic head is to the length of or to the distance of flow or to the distance between two wells in the aquifer is what is called the hydraulic gradient. And it is what is driving the flow of groundwater. Now, if the hydraulic gradient is going to decrease over time, it means that the difference is going to get smaller. So now we see that they're saying that the hydraulic gradient is going to decrease. Now we know at this point, if you're considering a steady flow, that is the drawdown is being constant, then it means that the at this point, if you check the hydraulic head of water at this point, it is going to be HR1. Now say the hydraulic head is going to reduce, then the hydraulic head is going to be HR2. Assume if that is what it means. This means that there is a value for HR1 minus HR2. I is reducing, which means that the drawdown is cannot be constant. So this value over here is changing, which is not a possibility. Because if hydraulic gradient is reducing, it means that there is a difference in the pressure head of water or hydraulic head of water at this point, which is not possible since this drawdown curve is constant. So if the hydraulic gradient was decreasing, it would mean that there would be a difference in these 2 points of level of water, which is again contradictory to the question. We are saying that drawdown is approaching a constant position. So there is no possibility for the drawdown curve or the hydraulic head to change, because in that case, it would result in a fluctuating drawdown position or drawdown value. So again, that option is also not possible. Then third option is saying the aquifer is homogeneous with uniform permeability, which is very close to the assumptions that we checked. They are saying that it has to be homogeneous in isotropic medium. Homogeneous means all of the soil throughout the material has to be uniform. Isotropic is when the properties at any point of the soil is going to be the same. So that means permeability, which is a property of the aquifer material, is also will be same at all points. That is what uniform permeability means. So that is one assumption of the steady state flow in unconfined aquifers. So the option C would be the correct answer. Again, option D, flow is turbulent. Here they say in pumping is at constant rate, drawdown is approaching a constant rate. So it is and at a with respect to time, which is indicative of steady state flow. Steady state flow is not possible for turbulent flow, so the flow cannot be turbulent. So option D is also not possible. Again, you can refer to the material for more understanding of it, and then further towards the end of the session, if you have doubts regarding this question, because it is a lot of assumptions and all to go through, feel free to ask. The next question: in a confined aquifer, which of the following is contributes to or has the greatest influence on the rate of groundwater? Is it the porosity, thickness, hydraulic conductivity, or viscosity of groundwater? You can provide your answers in the chat box, and then we'll move on to the solution discussion. Okay, moving on. A very direct question. So the rate they're talking about the rate of groundwater flow. Rate of groundwater flow is a function of hydraulic conductivity, hydraulic gradient, and cross-sectional area, not a function of the porosity, not a function of the thickness of the confined aquifer, and also not a function of the viscosity of groundwater. So correct answer would be option C, hydraulic conductivity of the aquifer. Again, which type of aquifer does groundwater remain under pressure greater than the atmospheric pressure because of being bounded by impermeable strata? This is a question from the previous lectures, which you should be familiar by now. Okay, I can understand the confusion in this answer. I think partition aquifer is also right. Confined aquifer is nothing but partition aquifer. So let me again confirm with why this answer is being provided, the solution, and then if there's any change, I'll be making the changes in the presentation and providing. So it can be either A or D. What is the unit of hydraulic conductivity when measured using the SI system of measurement? All of these units can be used, but what is the unit when it comes to the SI system? Okay. The correct answer is D. It is in meter per second. Relationship between hydraulic head and pressure energy. Correct. The answer is pressure energy plus elevation energy. Groundwater will flow from regions of dash hydraulic head to areas of dash hydraulic. What combination is the correct answer? Correct answer, it is from high to low. So that will be for today's session. If you have any doubts regarding today's session, I'll be here till 8 o'clock. Otherwise, you are free to leave the session. Thank you for attending. Vinod, do you have any doubts regarding any questions? Okay, in that case, uh, we can wind up the session for today. You can exit the session. You can leave the room. Thank you for attending to this class. So thank you everyone for attending today's session. We'll meet in the next week with problems, discussion of problems related to lectures of week 7. Should help you do assignments in week 7. So have a good evening. Thank you.